Good afternoon, ladies and gentlemen. So in this short video, I'm going to go through all the practice problems to prepare for practice A and practice B. So in your textbook number 68, you'll see problems 7 through 11 are for practice A. And then for practice B, it is number 16 and 17. So those are the ones we're going to do right now. So I have the textbook here. Hopefully you can see it. Number 7, it says a school bus takes 0.53 hours. So they're telling you it's 3 significant figures. 0.530 hours to reach the school from your house. If the average velocity of the bus is 19 kilometers per hour to the east, what is displacement? What is the displacement? All right, so let's go over vectors. Velocity has a magnitude and a direction. It's a vector. Displacement is a vector. It has a magnitude and a direction. So if the bus is going to the east, your displacement more than likely is also going to go to the east. So that's part of the answer. Because remember, vector has to have 2 pieces of information. 2, that's 2 fingers. The magnitude, how big it is, and in what direction. All right, so let's write down what we know. Always write down what we know. So the first thing, hopefully you can see it with this. Try this, I'm squishing a clipboard right here. First thing they tell us is that the average velocity is 19.0 kilometers per hour. Notice how I like putting the hour in a real denominator, not like a forward slash. It's just easier for computations. And they want to know, and they also tell you that it took how long? Your delta t is 0.530 hours. So if we wanted to, we could figure out how many minutes that is and how many seconds it is. But right now, it's 0.53 hours. So I'm thinking that's probably pretty good because the denominator over here is hours as well. And what are they asking for? They're asking for what the displacement is. So I want to know what delta x is. So as a reminder, what's delta x? What is delta t? Delta just means the change, So delta t is probably t final minus t initial. Like what time did you actually finish? You finished at 10 a.m. and you started at 9 a.m. So the delta t would be 1 hour. So delta x is x final minus x initial. So I'm using subscripts. F for final, I for initial. Okay, so this is what they gave us. So how do we know what the displacement is? So this is where you lean on something you already know. If you're driving or already learning how to drive, you know that speed is distance over time. So what's the difference between velocity? Velocity is speed with direction. Okay, so sometimes you're going to see this in the future, the little arrow on top of it, because it shows it's a vector. But we can think of it, the magnitude of the velocity is speed. Okay, so what exactly is V average? V average, the average velocity is the distance over time. All right, so that's something you already knew because you know it's miles per hour, so it's distance over time. But the question is, what is delta x? That's what we want to know, what delta x is. They gave us the V average, we know this one, and they gave us the delta t, we know this one. So how do we solve for delta x? Well, you remember in your algebra, this is algebra 1 now, if we multiply delta t to both sides, what happens? What happens is the delta t's on this side cancels out and we end up with delta x. All right. So delta x must be, I'm going to rewrite it, delta x must be V average times delta t. Now you could have written it the other way around, delta t times V average, doesn't matter, right? 3 times 2 is equal to 2 times 3, it doesn't matter. Okay, so now remember, if we did this right, our units should work out. So I want you guys to always put your units in, because then you'll see, oh, I did it right, or I didn't do it right. All right, so V average is 19 kilometers per hour. And I'm going to multiply it by 0.530 hours. I like fractions, so I'm going to put it over 1. You don't have to, but that way I know I'm multiplying fractions. All right, my hours cancel out, yay. And so now I end up with kilometers. So I take my calculator. You can see this here. I'm going to go 19 times 0.53, and I get 10.07. So what do I get? I get 10 equals 10.07 kilometers. Okay. And if you want 3 significant figures, that's about 10.1 kilometers. All right, that's it. That's it for the first one. All right, hope you guys can still see this. All right, let's look at the second problem. Second problem, number 8. Number 8 on the same page, page 68. It says, the Olympic record for a marathon is 2 hours, 9 minutes, and 21 seconds. I think that's pretty close to still true. My husband did a marathon in he had qualified in 3 hours and 20 minutes. Okay, so 2 hours, 9 minutes, 21 seconds. If the average speed of a runner achieving this record is 5.436 meters per second, what is the marathon distance? So how big is that distance? Kind of like the last problem. They're asking for a delta x, the displacement, and they told us the total time, and they told us the V average. Okay, so we need to write this down. You guys can see, so I'm going to see if I can push the book up. There we go. So what do we have here? We know that the total time is 2 hours. I'm going to leave off the significant figures for space. 2 hours and 9 minutes and 21 seconds. And then they gave us that the V average is 5.436 meters per second. You'll find that I put the word sec instead of S because my S's look like 5s. It's very confusing. So I finally decided to stop fighting it and just put sec. So I don't have that problem. Okay, so interesting. I have hours, minute, and seconds. Okay, I'm going to multiply stuff and I want the units to come out, but I needed to come out to seconds here, huh? Or you can convert all this to hours and then multiply it, convert it to seconds. So let's go back to what are we asking for first of all? We want to know what's delta x equal to. What's delta x equal to? So I always start with the equation. I want you guys to do that too. The equation we know is that the average velocity is delta x over delta t. Okay, but I want to know what delta x is. So I see that if I multiply delta t to both sides, I'll get delta x. Alrighty, so delta x is the average times delta t. So now I need to make sure all this delta t is going to be, will help me so things cancel out. I'm going to go ahead and write down here. This one's 5.436 meters per second. All right, so I need to get the seconds to cancel out. So we're going to have to convert all this business up here to seconds. All right, this one part is already in seconds. Let's do the 9 minutes one. Let's convert that to seconds. So 9 minutes, I want my units to cancel out. I know there's 60 seconds to a minute. All right, 9 times 6 is 54, so this must be 540 seconds. Is that right? 9 times 6. Can't find my answers here. All right, so the next part. What's the next part? So the next part is the 2 hours. Okay, not too different. So I have 2 hours. Let's do that again. This time I'm put hours to cancel out. So I have 1 hour is how many minutes? 60 minutes. And then I have minutes down here and I have 60 seconds. Eventually, maybe you'll remember that 1 hour is 3,600 seconds. But if you don't, 6 times 6 is 36. Okay, so 2 times 3,600 comes out to 7,200 seconds. All right, so my total time must be 540 seconds. I'll put a little box around here. Plus 7,200 seconds, plus the 21 seconds, plus the 21 seconds. All right, so I'm going to add this up. And here's the first time I think you guys see me use the word sigma. Sigma is a Greek symbol, the Greek, one of the letters, Greek alphabet for E. We use the word sigma, it's pronounced like this, sigma. And that's what we use for adding stuff up. So sigma faster waves. I add it all up, and I have to add up 540 plus 7,200 plus 40 plus 21, and I get 7,761 seconds. All right, so that's what I need to put over here. So over here, I'm going to multiply it by 7,761 seconds. Put seconds there. All right, now I got things to cancel out, and I can multiply that up. And what do I get? I get, what do I get here? I'm looking here in my math. I multiply those out, and I get 42,188.796 meters. All right. By the way, I recognize as soon as there's 1,000, that's a kilometer. So I'm like, ooh, look at that. It's 42.2 kilometers. That'll come with time for you guys. Let's see, for you guys, you could have said, oh, that's about 42,000 meters. And that's 42.2. All right, 42 point. I guess I could have said 42.2. 42,200 meters, and that gives me 42.2 kilometers. All right, so let me see if I can show you guys the whole problem. Here's what we did. So what did we do? We had to make the time be in 1 unit. So it was on your quiz. Everything has to be in units. Then you're allowed to add them up. So we just converted all that time to how many seconds it was. And because the displacement is the average velocity times the time, there's our average velocity that they told us, times the second, and we have to 42.2 kilometers, which is exactly true, by the way, for a marathon. All right, let's look at number 3, or the third one, which is number 9. This one's a really cool one, kind of fun. Let me see, can you read it first of all? All right. So one of the things I encourage you guys is to feel okay about rereading a problem. So I've told many students, if I have a master's degree and 2 bachelor's degrees, and I read a problem, I go, wait, what? And I read it again, that's okay. Usually when you read it again, you'll understand a little bit better. Maybe you'll have to read it a 3rd time. That's okay. The other thing I want you guys to feel comfortable with, besides rereading a problem, is to draw a picture. Always drawing a picture makes a big difference. And later on, I'll go through some problems from the quiz that only a couple people drew the Earth and the sun, and they were able to figure out that radius wasn't enough. You had to figure out the diameter, how many little moons instead. And if you draw a picture, these things just jump out at you as logical. Okay, so here it is, number 9. So 2 cars are traveling on a desert road, as shown below. After 5 seconds, they're side by side next to a telephone pole. The distance between the poles are 70 meters, and then they want to identify the following quantities. The displacement of car A, which is the blue one, after 5 seconds, the displacement of car B, which is the red one, after 5 seconds, and then the average velocity of car A during those 5 seconds, and the average velocity of car B during those 5 seconds. So it took me a little bit to figure this out. I had to notice that the car B, the red one, was next to this telephone pole, but car A was ahead of it. And I had to figure that out because over here, the time clock says 63 hours and 1 minute and 0 seconds. And the next one says 63 hours, 1 minute and 5 seconds. So I went, oh, okay, so this is the before picture and here's the after picture. Again, please feel comfortable rereading the problem. So the question is the displacement of car A after 50 seconds. So here's A, and in 5 seconds, it's at the next pole. The next pole. Why do I know that? Because I had to read it again, side by side, they're traveling at the next telephone pole. So I don't know why maybe it would have been easier if they had left this blank and labeled them, but anyway, you have to think about it. So this is the very next pole. All right, so the first thing I do, as always, is I draw a picture. And rather than me drawing the picture all over, I'm going to show you the picture I drew. Let's see if you guys can see my picture. There's my picture. So I can pull that down. So these are my, not very elegant, I know, telephone poles, and they're each 70 meters apart. from here to here 70 meters, from here to here 70 meters, from here to here 70 meters. And I drew another one because I still didn't get it, that it was the very next pole. So I went, oh, okay, this one has car B. I decided to just label B. So B is the red one, car B. And at this pole is car A. At the next pole, they're both next to each other 5 seconds later. Okay, so the first question is, what is the displacement? So let's see, how can I do this? Like this. You guys can see this. I'm going to push this up. You guys can see this picture here. And I got to move this paper up. Here we go. So the first question is, what is the displacement? They want to know, what's the displacement of car A? What's the displacement of car A? And I'm just going to put A. So what distance did it go? Let's say it started here. Oh, car A, sorry. Yeah, which one are we doing here? Well, I guess car A. Car A is over here. So it started here and ended up here. So what displacement did it go? Now remember, you could think of displacement as a distance when the distance is the magnitude of the displacement, but displacement does have direction. So we're going to pretend that north is up, so east is to the right. So the displacement would be, it just went from this pole to the other pole. It's 70. It's 70 meters. And I'm going to say to the right, because they didn't tell us east or west. So I'm going to say just to the right. Okay? So that's the displacement of car A. So what's the displacement of car B? I probably should get rid of the question mark. Well, let's see. Car B is the one further back and ended up 2 poles away. So we just add them up. 70 plus 70 is 140. So we know it went 140. Also it went to the right. Okay, so there's our displacements. But the next question was, what's the average velocity of car A during those 5 seconds? And the other one was, what's the average velocity of car B during those 5 seconds? So I'll move this up so you can see my little pictures again. Okay, so what exactly is average velocity? Let's do this. V average for anything is delta x over delta t. Okay, so for the first guy, V average for A, we need the displacement that A went. Well, A went 70 meters to the right. We can add that to the end. And then the seconds. Well, we know it's 5 seconds because they told us, and we see the little timer. So what is 70 divided by 5? 70 divided by 5, using your calculator, you'll end up with 14 meters per second. Now, we don't have to put to the right. We can also just say positive. Why? Because the convention is that positive is to the right and negative is to the left. Okay, so that's the car A. So what is my average velocity then for car B for that time frame? Okay, same thing, delta x over delta t. We already figured out the delta x up here. We know that the B car went 140 meters in that same time frame, 5 seconds. All right, so it's going to be double this guy. I didn't use a calculator. Oh, this is just double, huh? So also going to the right, I have 28 meters per second. Okay, there we go. Those are our answers for number 9. This one was number 9. Okay, number 9. Okay, so moving on to number 10. I'm just flipping the paper over so I have room here. Let's read number 10, and it's the top of the next page. I hope I can get this here. You can read it. I'll move my little Post-it note. Ooh. Okay, here we go. Fun word problem here. Number 10, it says, Sally travels by car from one city to another. She drives 30 minutes at 80 kilometers per hour. Then she drives 12 minutes at 105 kilometers per hour. Then she drives 45 minutes at 40 kilometers per hour. Then she spends 15 minutes eating lunch and buying gas. All right, good day for Sally. A, determine the average speed for the trip. And B, determine the total distance traveled. All right, so as I told you guys, the first thing you always want to do is write down what's given. Even if you don't know exactly what to do right away, I promise you, for some reason, when you write down what's given, then you write down some forms that you think that may apply, then it kind of jumps out at you. Okay, so I'm going to write this down. Let's see. I think I presented as a table what they tell us. The first thing they tell us is how long this person did this, and then they tell us what the velocity is, or the average velocity, let's say. Velocity, I'm going to put here just an arrow for velocity. Okay, so my first one, she travels 30 minutes for 80 kilometers per hour. And then she travels 12 minutes for 105 kilometers per hour. Then she goes 45 minutes for 40 kilometers an hour. Maybe there was a traffic jam. She slowed down way much. And then they tell us something which may or may not be interesting, and that is 15 minutes. She does lunch and gets gas. Okay, so we want to know average speed. We want to know average speed. So I'm going to write down here, what is average speed? The average is delta x over delta t. Okay, now because we need to know what the average speed is for the whole trip. So that means I'm going to need to know what delta x is for the whole trip. But we notice, she went different distances and different times here. Okay, I'm going to extend this line out because I see that I have an issue with units. So if I have an issue with units, we just need to fix the units. So I'm going to be multiplying stuff with hour. So maybe I should change the minutes to hours instead of changing the speeds to kilometers per minute. I happen to know that 30 minutes is equal to 0.5 hours, right? If you don't know that, you can go 30 minutes times 1 hour over 60 minutes, and that'll give you 30 over 60, which gives you half an hour. All right, the next one over here, I put the same thing, go, well, I know that's 12 over 60 hours. And then I use the calculator because I didn't recognize it right away that it's 2/10 of an hour. 45 minutes, ooh, I know that's 3/4 of an hour. And if I know that's 3/4 of an hour, then I can call that 0.75 hours. Okay, here's 15 minutes, so I don't know if I'm going to need this, but I'm going to put that that's 0.25 hours. Okay, so I'm going to need to know what the distance was in each time frame. So I could have continued here, figured that out, but I didn't. I did it underneath. So let's figure this out. Remember, to figure out delta x, I have to multiply delta t to both sides. So delta x is the average times delta t. That's what I need to figure out for each one. So you could just do another column and figure out with your delta x of each one. But I'm going to go a little slower here, put it here underneath here. So I'm going to rewrite it. Delta x is v average times delta t. Now, why am I saying v average? Because they average 80 kilometers, 30 minutes. Maybe they didn't go exactly 80 the entire time, but it averaged out to 80 kilometers per hour, those 30 minutes. So I'm going to leave it at v average. Okay, so for the first 30 minutes, what is it? Let's see, 80 kilometers per hour times 0.5 hours. Now, how nice, my hours cancel out, and I get 80 times 0.5, so I know that she went 40 kilometers in that first stretch. Okay, then the next, so that was first 30 minutes. Then 12 minutes, how far did she go? All right, I know that's what'd she go? 105 kilometers per hour. And she went for 2/10 of an hour. This, I always try to avoid a calculator when I can. I know 0.1 is 10.5 and 10.5 plus 10.5 is 21. You can use your calculator. 105 times 0.2, you get 21 kilometers. And then let's do the last 45 minutes. Last 45 minutes, what do I have here? 40 kilometers per hour. And she went 3/4 of an hour, which is 0.75 hours. My hours cancel out. And what do I get? I get 30 kilometers. Okay. So what is this total? 40 plus 21 plus 30, that's my total distance. I have 91 kilometers. And by the way, one of the questions they asked for here, the second one, determine the total distance traveled. Well, here you go. You just figured out the total distance traveled was 91 kilometers. Now we're ready for the first question. Let's see, I think I'll just leave it here, kind of move this over. All right, so the question is, what's the total V average? What's the total V average? Well, I always go back to my formula, the one that you guys already knew. For speed, velocity, speed is the magnitude of velocity, change in distance over change in time. The total amount of time, total distance, delta x, displacement is 91 kilometers. How long did she do it? Oh, I need the total. Oh, here's the total delta x and total time. Here's the interesting part. You get two answers depending on how you answer this. So I went here to figure out how long did this take? How much time was this? Let's see if I can highlight this. I went 0.5 hour, 0.2 hour, and 0.75 hour. So if I add that all up, let me bring it over here again. Put here, delta t total is 0.5 plus 0.2 plus 0.75. And you add that all up and you get 1.45 hours. 1.45 hours. So I had put 1.45 hours down here in the denominator. 91 kilometers or 1.45 hours, I get 62.75 kilometers per hour. Now, I'm not going to be worrying right now with you guys on significant figures. I just want you guys to know how to solve this. Then you can worry about that later. However, the book wanted to include bringing lunch and buying gas. Okay, and that took another quarter of an hour. So if that's the case, then you need to add another quarter of an hour here, and you get 1.7 hours, right? 2.5 carries over 1.7 hour. So if that, I'm going to say if you include with lunch and gas, then it's 91 kilometers over 1.7 hours. And then you get a different number, 53.5 kilometers per hour. I think that's silly, but in case you guys are looking for how come there's a different answer, that was why. I had to figure out why they had a different answer. But anyway, that's how you do it. So let me summarize that. Go back here. They gave you all this cool information. How long it took her to go at what speed. How long it took her to go at what speed. And then the stopping. Then they wanted to know what is your average speed for the entire trip. For the entire trip, I need to know how far you went. So we had to apply this basic equation of displacement based on the equation of average velocity. And we did it for each time interval. Then we got the distance of each time interval, we added it up. Then for our grand total average velocity, we just go back to the formula that we know, and that is what is your total displacement over total time driving. I guess they didn't say total time driving. They used the word the total trip. So I guess it included buying gas. And there you have it, and that is number 10. Number 10. So we only have one more to do, which is an awesome one. A really good problem. And that's our last one. And then I'll finish this video. And we'll do practice B on a separate video. All right. So let me see. I'm going to bring it up really big so you can read this one. Now, notice that it's a long problem to read. So this is like one of those good ones that I suggest you probably want to read it more than once. Okay. So here we go. Runner A is initially 6 kilometers west of a flagpole, and it's running with constant velocity, 9 kilometers per hour, due east. What does due east mean? It means they're going in the east direction, easterly direction, towards the east. Runner B is initially 5 kilometers east of the flagpole and is running with a constant velocity of 8 kilometers per hour due west, going towards the west. So in my mind, I'm picturing east towards the right and west towards the left. What will be the distance of the two runners from the flagpole when their paths cross? And then they're saying it's okay, you can leave it in kilometers, you don't have to convert it to meters. Okay, so no way to do this without drawing a picture. Well, there is a way, but I don't understand why you'd want to. So here's my little picture. Let's see if I can show you guys my picture. So I don't have to redraw it. All right, let's see if I can draw this. You guys can see my picture here. Hope you like my flag. I decided that Japan's flag is really easy, just white with a red circle. Okay, so here's my flagpole. And I decided to call this guy runner A, the one to the left, because he said it was to the left, wasn't it? Let's read it again. As runner A is initially 6 kilometers west. Okay, it didn't say west, it said to the left. Fine. So just for you guys who haven't memorized this yet, but you will when you're driving, if north is up, then you guys know south is in the bottom, and then it spells we. Okay, so west is to the left and east is to the right. So I knew that this guy is to the left of the flagpole because I decided north is up. And he's exactly 6 kilometers to the left or west of the flagpole. So I put 6 kilometers. There's my little tickies, 1, 2, 3, 4, 5, 6. There's my little guy. And he's going 9 kilometers per hour to the right. So remember, it's a vector, and so I show it as an arrow to the right. That's where he's going, to the right. But my other guy, he's 5 kilometers to the right. He's east of the flagpole. 1, 2, 3, 4, 5. He's to the right. And he's going 8 kilometers per hour. It's kind of hard for you to see. 8 kilometers per hour to the left. And I put negative in parentheses because when we want to describe a vector mathematical terms, we use signs. So to the right is positive, so therefore to the left is negative. So I know right away it's negative. So I put in parentheses because you don't want to do both. You don't want to have the arrow and negative because then you've got negative, negative, and you think, oh, it must be to the right. So that's why I put in parentheses. So this guy's going to the left at 8 kilometers per hour. So what's the question? Forget what the question is. What's the distance? You guys see that? What's the distance the two runners from the flagpole, where are they when they meet or when they are about to pass each other? When they exactly are passing each other, where is that with respect to the flagpole? Okay, so what do I want to do? Well, maybe you guys remember, hopefully you guys remember straight line equation. So I'm going to draw, you guys can see this, straight line equation. So I'm going to make time to be on the x-axis. Let me go down. Here we go. I'm going to make time to be on the x-axis, and I'm going to make displacement on the y-axis. Let me make this a little smaller. Okay, so what do I know? I know that the first guy, I'm going to write this down here. The first guy, let's say runner A, you guys can see this. Runner A is going, his velocity, because VA is plus 9 kilometers per hour. Plus 9 kilometers per hour, that's VA. And I know the velocity of the B guy, he's going to the left, and he's going 8 kilometers per hour. 8 kilometers per hour. Okay, so that's what their speed is if we didn't know the direction. All right, and we also know where they start. They're not starting at 0. So A, he's 6 to the left. So we're going to say that's negative. So let's see, 2, 4, 6. Here's which that guy is, that's my A guy. That's where my A guy starts. He starts down there. But my B guy, he's 5 kilometers. Let's see, 2, 4, 6. It must be right here. That's where my 5, that's my B guy. So he's at 5, and this guy here is at minus 6. All right, now, if you're going to the right, then hopefully you guys remember that your slope of displacement over time is velocity. That's what the slope means. So if I know that they're going, this guy down here on the left, the one on the left side, let's go back to my, my beautiful picture here. This guy here is going to the right, but he starts way at the negative side. So if he's going to go to the right, the slope is going to be 9 kilometers per hour. Okay, he's actually faster. So from down here, he's going to go, I'm trying to make it very steep. There we go. That's supposed to be steep. All right, so this is my A guy. He's going, and his slope is, what did I say, 9 kilometers. So that's a slope. So let me write that again. The slope is delta V. Why is that? Because remember that the slope is the change in the y direction versus the change in the t direction? And write that down. Change in the y over change in the x direction. I know I said t, but anyway. So here, it's my change in my x over change of t. Because the x-axis is time and the y-axis is displacement. Well, by definition, velocity is change of displacement over time. So that's the slope, is the velocity. All right, so I know that this slope is 9. Obviously, this is not being drawn to scale. All right, let's look at our other guy. Other guy, Mr. B. Mr. B, draw my beautiful picture here. He's going to the left. He's going to the left, so it's a negative slope. It's a negative slope. Okay, so, and this guy's not as fast, so I'm going to make the slope not as steep. So let's see if I can go like this, like that. There we go. So this is my B guy, and this is my A guy. So somewhere they met. They actually met right here. All right, so since you guys remember that the equation of a straight line is y is equal to mx plus b, you guys remember that? You remember that b is your y-intercept, and you remember your m is your slope. So I can write an equation for each of these guys. So notice we're expressing what these runners are doing with the mathematical equation. Okay, so let's write the equation for the first guy, the A guy. Here's my A guy. My A guy, y equals mx plus b. Okay, y is the delta x. Delta x is equal to m. M is my slope. So my slope for the A guy is 9 kilometers per hour times x, which is t, right here, t. Okay, but I have a y-intercept. So this guy, my A guy, is plus 5. He's way up there. Okay, he's plus 5. Okay, so again, do we know how to do y equals mx plus b? Okay, y is just whatever you're calling your y-axis, which here is delta x. M is your slope. They told us that this guy here is 9 kilometers per hour. Notice that if I were to put 9 kilometers per hour and time, if I have hours, okay, my hours cancel out, cool, and I end up with kilometers plus 5 where they started, and that'll give me my displacement. So that's how your units came out. Okay, that's cool. That's the first guy. Now my second guy, my B guy, got delta x is equal to, let's see, what's the slope? The slope is -8. X is time. And what is my intercept? My intercept is, oh, did I do this wrong? This guy here is down at the bottom, you guys. A guy, this A guy, so this is -6. Sorry about that. Got down by -6 for my A guy. Okay, my B guy is up here. So his y-intercept's on top, so it's plus 5. All right, so there's my equations. You guys remember 2 equations, 2 unknowns. Well, what happens when they meet? I want to know exactly what happens when they meet. Well, when they meet, the t of this guy is the same as the t of this guy. Okay? The t of this guy, that guy has got to be, well, I'm sorry, the time won't be the same, but we're going to be right, yeah, we'll be right here, the time. Whatever time this is, this guy will meet, this guy will meet. They're going to meet. So all we have to do is make these 2 equations equal each other. Let's figure out what that is, what that t is going to be. So I'm going to say all this guy over here is going to be equal to this guy over here, because that is exactly where these 2 lines meet. Okay, so the x and y values. You guys remember this from algebra? When I want to know where the 2 lines meet, I know that their x and y's are exactly the same. So the delta x's are going to be here the same, and the time's going to be the same. So where is that? Well, all we have to do is set these equal to each other. So let's do 9t minus 6 is equal to -8t plus 5. This is so awesome way to solve this problem. Okay, so there's our equation. So all we have are t's, and so we can solve for t. All right, so what do I want to do? Well, I see that if remember, math, you can always solve the problem more than one way. But if I add 8t to both sides, then I'll end up with the positive, I'll get rid of t's over here. There we go. I add 8t to both sides. Okay, so 9 plus 8, I get 17t. All right, so now I have 17t minus 6 is equal to 5. All right, but I want I want to get rid of this 6. So I add it to both sides, add 6 to both sides. And now I have 17t is equal to 11. So t must be equal to divide both sides by 17. 11 divided by 17. Huh. So I use my calculator, and I'm going to tell you guys why I don't want you guys rounding things off. Don't round off to the very, very end because you're going to add error. Anyway, here's what my calculator said. So that is exactly when they met, at a little more than half an hour, 0.647, et cetera, et cetera. You can figure out how many minutes that is. The reason I want to leave it that way is because now they ask for where is that? What is your delta x? So you can go back and plug it into either one of these because you'll get the same thing. So let's do the first one. Let's go and plug it into the first one. So the first one, my delta x of a, you guys can see that, delta x of a is 9t minus 6. So I'm just going to plug all this whole long thing into the t. Okay, 9 times all that stuff. And then I subtract 6 to it, and I get a negative 0.17647, what is it? Kilometers, right? Yeah, kilometers. Okay. All right, now you can round it off. So when you have to keep computing, you only want to round off at the very end. So I got negative 0.18 kilometers, or if you only had, looks like only one significant figure, so about negative 0.2 kilometers. So what does negative mean? What does negative mean? It means it's to the left of the pole, the flagpole. To the left of the flagpole by 0.2 kilometers. Now let's say you're like, yeah, I'm not so sure it would have worked if I used the other equation. So let's do it then. Proof is always good. So what is it for the B guy? The B guy is negative 8t plus 5. So I'm going to go negative 8 times that huge number right here, all that in here. That's why you leave it in your calculator. So I want you guys to have your own calculator, scientific calculator, and plus 5. There you go, all that. Plus 5, and would you believe it, lo and behold, you get the same thing, negative 1.7647, etc. So that's about negative 0.2 kilometers. Okay, so we finished all the preparation problems for practice A. On a separate one, I will do the ones for practice B. Let's review this one again. There we go. It looks like it didn't go any smaller. Okay, so bottom line is all those words that we read in the problem can be translated into equations. I know that a velocity is also a slope of a line. Slope of a line if I'm graphing displacement versus time. The first guy was 9 kilometers per hour in the right direction or east direction, and the next guy was negative 8 in the left direction or in the western direction. And then they told me exactly where they started. They didn't start at 0. This guy was 5 kilometers to the right of the flagpole, and this guy was negative 6 kilometers to the left of the flagpole. So I had enough information to draw the lines of the direction of their run. You can call it trajectory of their motion. And they wanted to know, well, where did they meet? Well, where they met is exactly where these lines meet. Exactly where these lines meet, right here. As you guys remember from algebra, that if I take two equations, two lines that I know intersect, and I make them equal each other, then I'll get the coordinates exactly of where they met. And that's exactly what we did. So we just made those equations equal each other. And then we solved for t, so we knew exactly what the t was right here. It was about a little over half an hour where they finally met. And then we could plug it in to figure out what the displacement was for this guy from the pole, from 0. Because this guy went farther. He went from here to up here, and this guy didn't go as far from here to down here. So from 5 to, what is this, 0.2. Anyway, all right, so let me know if you have any questions on this problem, and I will see you next time. See if I can figure out how to stop this now. Okay.